machines for exploding chemical spaces. So we try to pursue our mantra of picking purchasables fast and in a green way. So perhaps a few of you are not quite familiar with the concept of those big chemical spaces. Essentially, the idea is to use and exploit combinatorial chemistry to create huge chemical spaces, very simply put. What's that like? It's a little bit like assembling Legos, and there are pioneers in the field, notably Ukrainian Enamin, who have just recently announced to have opened an office in Germany, or a lab space and offices in Germany, in Frankfurt. Very welcome to our home country, the Enaminers. And there is a distinction between spaces that we usually do, which is non-enumerated, so exploiting the combinatorial nature of things, and databases that are enumerated. The issue with enumerated compound collections is that at one point it starts to get really, really hot, a little bit too hot to actually do the computations. So when we go to collections of sizes 10 to 10s, 11, 12s or so, you already see what amount of energy and effort needs to be put in to actually arrive at meaningful computations or at completing the job in the end. So for example, 2,900 GPUs were used to convert a set from 2D into 3D, a set of size 10 to the 10th, or a chemical space, if you wish. So all these numbers we didn't invent, but they had been reported in a very, very nice symposium on ultra-large databases at the very end of 2020. And there is also something on YouTube. We'll make available those slides so that you don't have to jot down now all these crazy links with SX, WPU, and so on and so forth. And also there is a very comprehensive review by Wendy Orr that has been deposited on the NIH web pages there, and on archive, I think, on Chem Archive. So BioSolveIT have the claw machines to generate and navigate those chemical spaces and pick out what you are hunting. And the most recent review that I'm aware of that covers all these things is by Korn and Matthias Raray and a few others, including myself, in Current Opinion in Structural Biology, which appeared this year. So just have a check there if you like. Part 2 of the intro slides, and that's the last part. Hope I don't bore you too much that are into that field already quite a lot, is that Lego part. So on the one hand side, we have building blocks that the providers have, that you may have in-house. And those building blocks carry functionalities, carry functional groups. And these functional groups can be encoded in terms of their compatibilities with respect to other chemical groups. So for example, that bromine here connected to an aromatic ring may react with an OH group on an aliphatic ring, as this example. So red may go with orange, at red, Lego may go with red, orange, and all this is encoded in this compatibility matrix. Certainly this only makes sense if you have the proper reaction definitions that actually exploit these functionalities on those molecules. We have a piece of software that is called Colibri, or a collection of software pieces in the Colibri suite of tools that takes care of the bookkeeping, that parses the reactions, does those transformations, knows a lot of reactions, etc., etc. Once you're done with this, you arrive at what we call the chemical space, or a chemical space. So the chemical space is essentially an assembly of building blocks and reaction descriptions. That said, we have several challenges with these, and I'm going to pick out 2 of those big challenges today, namely the first one being the size of those chemical spaces being continuously going up and up and up, so the sizes are surging, and we need to get compounds somehow, somewhere into 3D binding sites in the end. So the following slides will be split into these 2 chapters, if you wish, of this talk. So chapter 1, sizes, chapter 2, 3D binding site problems. Here's an overview that Alex prepared a little while ago, but it's still up to date. So I didn't mean to say that it's long ago, but that's pretty up to date, chemical space size update. And what we have here is we have on the x-axis, or on the any axis if you wish, because this is like an explosion here of planets, we have the number of molecules that these chemical spaces contain. Certainly, with 10 to the 26, on the one hand, we still are only a drop in the ocean. Chemical space has been oftentimes cited to be well above 10 to the 60th. So with GSK being the front runner here with 10 to 26, that's one side of the other of the coin. But the other side is those spaces here are still essentially purchasable. So we have Enamine, the front runner in terms of this idea. Ottawa, also in Ukraine, we have MQ, ChemSpace, Wuxi, E-molecules, and so on and so forth. And you see the red ones are those that have started to embark on their own corporate collections. And notably, I don't want to downplay this, Pfizer, Lilly, and others, Johnson & Johnson, they had already very early on very similar ideas that they pursued using also software searching. So these chemical spaces actually get bigger and bigger and bigger. And if we just look at what I told you about last year, when I also presented a very similar figure, we see that Enamine's real space has grown just since that presentation in May 2020 by 7 billion. E-molecules explore spaces new with 7 trillion, Wuxi 5 billion, and so on and so forth. So in total, we have an add-on of 7.135 trillion new compounds since last year. That's pretty impressive and breathtaking, and puts challenges onto us. So those of you who are familiar with BioSolveIT software may be aware that we have the feature trees claw machine, so the feature trees algorithm, originally authored by Matthias Raray. And this has been partly rewritten, augmented, updated, and so on, maintained as a part in infiniSee, our chemical space navigation platform. What does feature trees do? Essentially, it hops farther away than you would usually perceive with your eye and finds something which is still similar in terms of chemistry and physical chemistry behavior, chemical behavior. So Q is query, and we hop further away, we hop far away, we're distant yet similar. The new AnalogHunter software, which is also included in infiniSee now, is using a claw machine called SpaceLight. So the algorithm is SpaceLight, which is also originating from the Hamburg ZBH University at Raray's group. Louis Bellman is the author here. And what this does is it finds close analogs. So it's like, it acts like a magnifying glass and checks in the vicinity of your query compound what's going on there. So let me give you a few examples so that you get a feeling from the MedChem perspective what this is like. So here we have a query, Sorafenib, and we have the similarity that the infiniSee claw machine SpaceLight picks out. So essentially it's straight away comparable to ECFP4s that you know from perhaps other tools that you may have been using in the past. So here's Sorafenib. It is actually found as such directly with an identity score of 1 in the real space, but it is also found as slight modifications with 0.85, 0.81, 0.79, and you see those modifications are really subtle. So instead of a 1,4 substitution, we find a 1,2,3 substitution, we find an inserted methylene or a simple fluorine. So these ECFP4s do deliver close analogs. Of course, certainly high similarities are then needed or are entailed. The compute time is actually seconds, so it's very, very fast. You can use it straight away, click and go. However, when we go to somewhat smaller similarities, so 0.6, 0.48 or so, you see that the ECFP4s also capture parts of the molecule, let's say. So in this case here, for example, all the thiazole ring or the methyl substitution on that ring is essentially discarded and only the methyl survives here. But essentially this molecule is already relatively different compared to the original query. And this one here is found in Wuxi's galaxy space, or galaxy as you may want to pronounce it. Also here, there is a significant difference in the molecular structure here, and this is reflected in lower scores. If, however, we switch the claw machines now and we go over to the feature trees algorithm that is more fuzzily searching, and then we look at the top scorers, I should stress these two are the top scorers of those two respective spaces here. But if we change the way that we jump or navigate through chemical space, then at high feature tree similarities, we find something like this. 0.9 0.969 feature tree similarity in the explore chemical space. So the E molecules chemical space looks a little bit kind of interesting, let's say, at first sight. And this one here from the real space. And please note, once again, in case you didn't know before, feature trees are agnostic to automata para substitution patterns, which is why I put the fluorine substituent as such on the right-hand side here. So these molecules still share a difference, but it's often not so obvious. So what I mean to say with all this is the AnalogHunter, the new claw machine in infiniSee, the SpaceLight algorithm, which is the name of the algorithm underneath, it acts like a strong magnifying glass around a query. It does find those analogs if they are in the space. If they are not in the space, it can certainly not find it because it's like a very sharp knife that carves out the vicinity of your query molecules. Lower similarities often indicate matched substructures. It is very fast. It just needs very few seconds on purely combinatorial spaces. So sometimes you may want to add an enumerated list of molecules to your chemical space. And in these situations, certainly, then the machines will get a little slower, but they exploit the powers, or they can play out their powers when we have the combinatorial character underneath. So in essence, we would ask you to apply these machines according to your use case. So depending on what you would like to have, would you like to find close analogs, or would you like to hop distantly and still retain some similarity? In essence, everything will profit from the space sizes being even larger. So chapter 2, we are now going more and more into the 3D area. The first successful applications that exploit combinatorics have been now published. Agnostic chemical space docking, so chemical space docking binding site and a bunch of ligands or a chemical space. Paul Berosa talked about this last time, and Gastreich's group, Sadibekov et al. From UCLA, published something in Nature 2 years ago, Fragment Evolution into Chemical Space. So starting with the fragment and then evolve this, let this grow into chemical space. I'll speak about this on the next few slides a bit. And infiniSee searching, then docking. So kind of a pipelined approach also to tackle these big spaces have been published now. So the first example is Fragment Evolution into Chemical Space. So this was a collaboration with Gerhard Klebe's group at Philipps University in Marburg between ChemSpace, Enamine, and Crystals First, were a spin-off of Gerhard Klebe's group. And you see here that we started from 4 fragments that could be co-crystallized. These were weakly binding fragments. We took those and checked where potential anchors or exit vectors, if you wish, were to get our chemical space docking ignited from. So it was like posing a seed fragment and then continuing to build up the molecules that the binding site would select from the big chemical space back in the months, 2 billion, 2.6 billion. We obeyed the enamine real space compatibility, so the chemistry that these fragments could undergo was respected in combination with the binding site picking out the molecules that would bind well and fit well. We retrieved 40 actives, of which even 6 could yield X-rays of very nice quality. As you can see, the resolution is really convincing. It's been published late in 2020, volume 65, page 1563. So what is so different about this? Well, usually you are presented on such slides funnels. So that means you put big stuff in and you get smaller and smaller and smaller, and some actives drop out at the end. In this case here, we only used the X-rays and grew into this perturable space. We did not use any sort of affinity guidance. In hindsight, this wouldn't even have worked because the fragments were binding too weakly to actually be detected in classical assays. So 4 we started with, and then we blew everything up with this fragment docking and the partial library enumeration that these fragments could undergo. And then we docked those full molecules template-based onto the initial fragment that was posed, did scoring, filtering, and then the classical monkey business of visual inspection, synthesis, and so on and so forth. This actually was attractive enough to make it as the cover of one of those Journal of MedChem issues, and also their globe picked it up in his In the Pipeline blog in September 22 with the title Crystal Fragments. If you would like to read what he has to say on this, then it's on Science.org content blog post Crystal Fragments. And I want to take this opportunity to say hello and happy birthday to Sergey Glinka, CEO of Crystals First, who has his birthday today. Example number 2, infiniSee space searching and then docking. So actually the graphical abstract of this paper is almost sufficient to understand what was going on, but we'll look into this in a little bit more detail. What is absolutely striking for me is the speed that these colleagues actually delivered. So this paper was published in March 2023, and it must be roughly 6 months between the early virtual screening to this publication, because the tool that they reference there, the tool version of infiniSee, was only out roughly 6 months before. They found tenfold activity compared to the lead then, and even went into xenograft models and assessed the tumor volume and saw how these would shrink. So what did these colleagues then do? Essentially, they used literature molecules and used these as query molecules in infiniSee, used the Peachtree's claw machine, so the Peachtree's algorithm, and did a chemical space search across all spaces that were back then available, in total a size of 10 to the 12. They arrived after docking and selecting in the order of 10 to the 4 molecules that they then docked with Autodock Wiener. They arrived at a lead compound that they were able to crystallize, and this PDB has actually just been out a few days ago. And they could rapidly optimize this lead compound with just small modifications. Look, there is the introduction of a nitrogen, the fluorine got lost, or the fluorine hopped over into this position. They could arrive at a very low single-digit nanomolar inhibitor in a cell assay. So the speed is really striking, and I'm amazed by the amount of work that has been done in the context of this paper. So now let me talk a little bit about big data in changing environments. So if this is us, a human researcher, then we have experienced quite some changes during the last few months and years. One of the changes being that we don't talk to just our colleagues in the same science, but we have various sorts of audience. We have these webinars that we now have on a very regular basis. Something like our DrugSpace symposium, something like this has not existed in this form before. We certainly talk to clients, but also more and more investors are interested in seeing appealing material, appealing results, nicely presented, and all sorts of peers. So the way of communication has changed, in my opinion, during the last few years. But what also has changed most certainly is we've had a pandemic, and we have a lot of computation outsourced now. So what has not been accepted at all, I still recall several pharma colleagues telling me we would never output or put any of our targets into the cloud. This is now widely accepted. Lots of things have changed. So the communication between the researcher and the calculation platforms have definitely grown and become much, much more important. And the pandemic has also brought with us that we sit at home sweet home. So all this has imposed changes in the way how we need to communicate with others. And in addition, we also have a much more risen, much higher, at least I can say that for us here in Europe, much higher awareness for green computing and energy awareness, footprint awareness, etc. So let me quickly look at this from a different viewpoint, namely from a computation viewpoint. So the pandemic has kicked us back home. That means it would be wishful and very nice to do lightweight computation at home with meaningful results. Point 2 is the communication with peers and other interest groups is still key and has changed. So it would be nice to save time there, drag and drop stuff, get access to graphics easily, and also include this with interactive 3D demonstrations and so on and so forth. Cloud computation is now accepted and surging, growing. So things like the API implementations that we have heard before is something which is definitely of importance to the community, and the footprint awareness is also growing. So we still need to pursue lightweight algorithms and not go brute force, at least in our opinion. So I'll give you an example of how we view this part of the world. We have now the scaffold hopper that I mentioned before, which essentially translates to the feature trees engine that you can compute with an infiniSee on your local machine. If you hover with your mouse over this respective button, you will see that it changes and it gives you the possibility to actually run this on an external server. That optional REST package is available from us. So what does that actually look like? This is infiniSee. There is the mode selector at the very top. You hover over the scaffold hopper icon, either compute on your local machine or choose to go to the external server. Once you're there, it quickly checks for the chemical spaces that are available. You then drag and drop your SMILES file, your SD file, or whatever file is accepted. You select one of the spaces that you would like to go for. In this case, for example, the Wuxi Galaxy space. And you may even impose some pharmacophore-like features or constraints. So I need to have a minimum similarity for this. Press a button, there are the results. I did not crop this video. It is really in real time. Yeah? So you can verify that the computation is actually set to be run on an external server. And this can be tested. There is a little test button on the right-hand side, but with this, essentially, you're done and dusted and can then browse the solutions and look at why the computer thinks something should be like something else, with this color coding.
Markus, you have 2 minutes left.
Thanks very much, Alex. So the next thing that I wanted to quickly show you is dragging and dropping things and saving time by proper by a proper communication between you and your peers. So in this case, on the right-hand side, we have CISA. So the 3D modeling suite that you may hopefully be using every day many, many times. You simply take a right mouse click, drag this over into PowerPoint. Often med chemists like to have the 2D sketches in the corner of a piece of paper, so you can drag this down there. But you can now do exactly the same thing with the 3D part. So there is a little menu entry under the utilities, which lets you export a 3D scene. And once you have exported this, given it a name, for example, my 3D, oh no, not my new E-model Mercedes, I wish I had, my 3D model it is, and save this, and then open your Explorer, or on the Mac, it's the Finder, and drag and drop this model into PowerPoint. Wait a second, and now you're there. You have something interactively rotatable, zoom inable, and you can increase the space of this or the size of this a little bit. So now very easily and within a few clicks and very, very little time, you have a very appealing and even interactive graphic to communicate with your peers, clients, customers, investors. There is a turntable functionality in PowerPoint that lets you run this while you don't even look at it. So with those 2 minutes going down to 1 minute probably, I'm already at the end. So this is the summary slide. I would like to have conveyed that on-demand chemical spaces get bigger and bigger, which is good because there is new and more chemical matter in there. And we are confident and very positive that we can still navigate this for quite some time. So we're fine with these spaces getting bigger and bigger. Please let them grow. We are very hard on productifying further on the 3D docking and scoring engine, which is not yet a product. So this fragment growing is currently available as a service from us. And we are very, very much energy aware and focus on algorithms that do not consume too much energy so that remote work, home work can continuously be progressed and pursued. Thanks very much, everybody.